Hello, and welcome back to our series on electrical and computer engineering. Tonight our conversation is about topology and electric circuits. According to Wikipedia, topology is an area of mathematics that deals with shapes, and in particular with the properties of those shapes that will not change if we fold or shrink or stretch that shape. Those are called the invariants of the shape. If we want to identify those invariant properties of an electric circuit, it is better if we make abstraction of the little distractions that are the resistors and inductors and capacitors, batteries, whatnot, and concentrate on the actual shape of the circuit. When we do that, like in this circuit, we realize that that circuit looks pretty much like a fisherman's net. And in a fisherman's net, we identify two invariant properties, two properties that will not lose their identity if we fold or stretch or shrink that net. Who are they? Well, this one and that one. The knots are invariant properties of the fisherman's net. And what about this one? Well, that is not really a proper knot. That is a repair knot. And you see, a repair knot does not affect the shape of the network. So it's a kind of a second-class citizen in the world of knots. The proper knots are those that are the joint of three or more of those filaments. Now, the other invariant property of a fisherman's net is this, the thread. Knots and threads, the two topological properties of the net. A thread is a link between two proper knots. A thread may have 0 or more repair knots inside. The one here in the figure has one repair knot, but the neighboring thread has no repair knots at all. When a thread has no repair knots, we call that an atomic thread. Now, those properties can be transferred directly vis-a-vis to an electric circuit. So the electric circuit has the same two topological properties, knots and threads. Threads and knots, but no. We had to use different names for the same two properties. In an electric circuit, instead of knot, we use a fancy word for knot. The Latin word for knot, node. Those are nodes in electric circuits. And the repair knot becomes a binary node. Repeating, binary nodes do not affect the shape of the circuit, so we do not actually pay that much attention to them as we do of true nodes. And the thread becomes now a branch. A branch is a link between two proper nodes. A branch may have 1, 2, 0 binary nodes. When the branch has no binary nodes inside, we call that an atomic branch. Let's have a look at that again from a different perspective. Every element that we've introduced so far has had two terminals, like this one, terminal X and terminal Y. Now, when we take two elements by one terminal and connect those terminals together, the junction of those two elements, terminals, is called a binary node. Fine. But if we have not two, but three or more, in that case, what we have is a true node. When we join one terminal of three or more different elements, the junction is a true node, or simply we call that for short a node. A comment: a node includes the wires spreading from the point of junction. Check this out. Is this a node? No, the node includes the wires. All of that is the node. To emphasize that, let's have not 3 but 5 elements connected together, like here. We still have only one node of connection, spreading through the wires that spread from the point of connection. One node. Now, to total time, let's see if we have communicated in this circuit. I'm going to ask you 2 questions. How many true nodes can you identify? How many binary nodes can you count? I suggest that you pause the video, you do your math, and then you resume and compare your answers to mine. Let's begin here. There is a node here, the junction of these three elements. Well, but that node, of course, includes the wires spreading from the joint. All of this is one node. I will identify true nodes with numbers. This will be node number 1. And how about this one? Well, this is also a node, right? Yeah, so but this node includes those wires. All of this is one node, and this would be node number 2. And the third one, the one on the far right, node number 3, including the wires. Always include the wires. Soon enough, you will not have to actually do the drawing, but in your mind, you will identify those nodes. Here we have a 4th node. See? Here, 3 elements connected together and the wires arriving and leaving it. That's node number 4. There is one left, the one at the bottom. All of this one, yeah, but that includes the wires that spread from it. All of these is one big node. That would be the node number 5, the true node number 5 of this circuit. And those are the 5 true nodes in the circuit. Let's go now for the binary nodes. Here is one. Let me use letters for binary nodes. This is a node A, a node B, a node C, and D, and E, and F, this one, and G. We have 5 true nodes, and we have 7 binary nodes. Is that what you got? Excellent. 5 true nodes and 7 binary nodes. By the way, it's customary to number nodes not from 1, but from 0, 0, 1, 2, 3, 4, but still 5 nodes. Let's go back to definitions. The definition of a branch. A branch. What is a branch? A branch is the equivalent of a thread in a fisherman's net. It is a path that joins 2 nodes, 2 true nodes, mind you. It begins and it ends also in a true node. A branch visits at most 2 true nodes. 2 elements that share a binary node are in the same branch. A branch is a group of all the elements that share the condition above. That would be a more mathematical definition of a branch. A branch is often limited by a true node on each end. There is an asterisk call there. A single element connected to 2 true nodes constitutes also a branch. The other definition we've used before is a branch is a path between 2 true nodes, but that is kind of weak, even though you and I know what I mean. An atomic branch is a branch that has only one element in it. It has only one battery or one resistor or one inductor or capacitor, but only one. That is an atomic branch. It has no binary nodes. The asterisk refers to the one exception to this rule that a branch begins and ends in a true node. Tutorial time. In this circuit, how many branches can you identify? Well, we'll identify a branch by the beginning and ending node, and in between the binary nodes it travels, right? So you see the one at the top is the branch between nodes 1 and 3, and it's a branch 1AB3. 1AB3. And then we have 1C2. And then it is atomic branch between 2 and 3. 2, 3. And we complete the count. Here we have at the bottom between nodes 1 and 4, 1D4, 1D4. And between nodes 2 and 4, 2E4. And 2F4. And this atomic one between 3 and 5, 3, 5. And 5G4, and the last atomic branch between 5 and 4, 5,4. So we have 3 atomic branches, 2, 3, 3, 5, and 5, 4. We have 9 branches all counted. Was that your count too? I'm sure it was. Now, let's define when we say that 2 elements are in series, a topological definition for series connection of elements. 2 or more elements are in series if they are in the same branch. Simple, bulletproof. Question: are those 2 elements, this battery and that inductor, in series? Let's see. 2 elements are in series if they are in the same branch, right? Those 2 elements are in the same branch, then they are in series. Yes, they are in the same branch. Therefore, they are in series even though they don't touch each other. Question: are these 2 elements in series? This resistor and that inductor? Of course, they are both on the same branch, so they are in series. How about those 2? Well, those 2 are in different branches, so they are not in series. What about these 2? Well, those 2 elements are in different branches, so they are not in series. Now your assignment. In this simple circuit, I want you to tell me what elements are in series and which ones are not. B and D, this B and this D, are they in series? Those 2 resistors? They are in the same branch, so they are in series, right? What about F and G? F and G, are they in series? No, they are in different branches, so they are not in series. F and G are not in series. How about H and E? This H and this E, are they in series? No, they are not. They are in different branches. E and G, this one and this one here, are they in series? No, they are not. They are in different branches. They are not in series. E and F? E and F, yes, they are in the same branch, so they are in series. Now let's go into another topological definition: parallel connection. 2 elements are said to be in parallel if they meet 2 conditions at the same time. First, both elements must be in atomic branches. Second, both atomic branches must share the same 2 true nodes. One of those conditions fails, the 2 elements are not in parallel. Both must be met. So, tutorial time. Let's have a look at the circuit that has 6 true nodes, identified from 1 to 6, even though I've told you that it's customary to start counting from 0. But this is our first lecture on this counting, so I'm using 1 to 6. Are these 2 elements in parallel? What 2 elements? These 2, S and T. This one here and this one, S and T, are they in parallel? Let's see. T is not in an atomic branch, so T cannot be in parallel with anything, and the answer is no. No, T is not in an atomic branch, so they are not in parallel. But if you thought that they really were in parallel, some of you might, I've seen that in class, oh, S and T are in parallel. No. What happens is that you are thinking, oh, I'm going to combine T in series with U, and the combination will be in parallel with S, right? No, but that is not what I'm asking you. I'm not talking about the future. I'm asking right now. Not in the future, but right now. The following example is both cruel and ridiculous. Why do I insist on that? Because we humans never forget cruelty, and we never forget ridiculosity. I promise this is a real word. I approach this unfortunate fellow in the street and ask him the very cruel question, "Sir, are you rich?" He looks up at me, smiles and says, "Yes, sir, I am rich." And I ask him, "How can that be?" And he responds, "Well, you see, I know I will meet a rich heiress and marry her, and then I will swimming in doubloons like a regular Scrooge McDuck." No, it's not in the future. Are you rich right now? No, you're not. So I asked you the question, Mr. T, are you in parallel with S? Right now, are you? No, sorry, I am not. It's only after I marry you that I know. But right now, I am not in parallel with anyone because I am not in an atomic branch. How about P and R? Where is P? This one. And this is R. Are they in parallel? They are in atomic branches, right? P is in an atomic branch. R is an atomic branch. That is the first condition. But those two branches must also share the same two true nodes. This P is between nodes 3 and 5, and this R is between nodes 4 and 6. So they do not share nodes. They fail the second condition. They are not in parallel. They are not. Now, how about Q and R? These two. Yeah. Q and R are in atomic branches, right? Right. But they share only one true node. They share the Q is between nodes 5 and 6, and R between nodes 4 and 6. So they share 6, but they don't share the other nodes. They must share both nodes. So they share only one true node, so they are not in parallel. Q and R are not in parallel. Oh, one more. How about N and R? There's N on the far right and R in the left of the circuit. Are they in parallel? That seems to be far-fetched because they are pretty far from one another. However, both are in atomic branches. N between nodes 4 and 6 and R between nodes 4 and 6. So both are in atomic branches and they both share the same two true nodes 4 and 6. They are indeed in parallel. Surprising, eh? R and N are in parallel. Who else is? Well, check it out. R, S, and N and X, all of them are in parallel, right? They are in atomic branches and they share the same two true nodes 4 and 6. Those ones. Who else is? M and K. Those two are in parallel. Check it out. They are in atomic branches between nodes 2 and 4. Good. M and K. Who else? I told you R, S, X, and N. The 4 of those elements are in parallel. Who else? Q and V. This Q and this V. Both in atomic branches and both between nodes 5 and 6. They are in parallel. Cool, huh? Let me dispel a misconception that we've been carrying around, perhaps from our days in high school. Not that the prof taught us that way, but we somehow concocted the idea that if two elements have the same current, they are in series. Wrong. But if two elements have the same voltage, they are in parallel. Wrong. Those are consequences. It is true that if two elements are in series, they carry the same current. It is true that if two elements are in parallel, they have the same voltage. But it works only in one direction, not in the opposite direction, as we shall see. Those are consequences. Those are not conditions. Two elements in series carry the same current. That is right. Two elements in parallel, they share the same voltage. We have to prove that, but that is in the future lecture. Those consequences cannot and should not be used as conditions. Two elements with the same current value are not always in series. And two elements with the same voltage value are not always in parallel, all right? Let's see what I mean by that. A little bit of logic. If condition A implies condition B, that is, every time that A is true, B is also true. That doesn't mean that when B is true, A is true. No. A implies B, but B does not imply A. What is true is that if B is not met, A is not met. If B is false, that implies that A is false. That is true. And you say, what? Let's do that with words. X is a dolphin. That is condition A. That implies condition B, that is X can swim. If X is a dolphin, X can swim. Can we say that if some Y can swim, that implies that Y is a dolphin? No, absolutely not. I can swim, I am not a dolphin. But we can say, if some element Y cannot swim, for sure, that is no dolphin. You get it? Now, let's see. If A implies B, it is not true that B implies A. What is true is that not B implies not A. Now, for circuits, M and N are in series, two elements, right? That implies that they have the very same current. Now, can we say that if two elements M and N have the same current, then they are in series? No, absolutely not. What is true is that if M and N have different currents, they cannot be in series. I think I made this clear. Consequences. Two elements in series carry the same current. Two elements in parallel share the same voltage. Those are consequences. Beware. Very often, elements are neither in series nor in parallel. Very often, most of the time. A and J, these two, A and J. They are not in series because they are not in the same branch. They are not in parallel because A is not in an atomic branch. What about this circuit? This circuit has to do with the asterisk that I showed you a moment ago. There are no true nodes in this circuit. What gives? Well, is there any branch? Is our natural question. Every circuit has to have a reference for voltages. We have seen that before. So what we do is we take one of those binary nodes and we promote that node to true node and name that the chosen reference for voltages. I've chosen the one at the bottom. That's my reference. And now it's a true node. By decree, I have promoted it. So a circuit has at least one true node, one by decree in this case. And that one node is the beginning and the end of the single one and unique branch in that circuit, right? The branch is reference ABC branch. So you see there you have a branch that ends and begins in the very same true node. And that is the end. I hope that you enjoyed watching this video as much as I did while I was preparing it. I wish you all a very good evening. Thank you very much.